Hello everyone, my name is Tabassum. Today I will be presenting our work, ConfD, Analyzing Configuration Dependencies of File Systems for Fun and Profit. This is a joint work with my colleagues and my advisor, Dr. Zhang. File systems are essential. For example, it manages files and also serves as local storage for many distributed systems such as BGFS, Hadoop, Lustre. File systems have many configuration parameters to meet diverse need of data management. On the left-hand side, we show an example where Ext4 allows user to store a file larger than 2 GB in the file system when large file feature is enabled. On the right-hand side, there is another example where DAX feature in Ext4 enables user to have direct access to NVDIMM devices. Many popular file systems such as Ext4, XFS, UFS, USENIX follow modular design and can be configured via different utilities in general. For example, Ext4 can be configured using make2fs, mount, e4defrag, e2fsek, resize2fs, and many other utilities. Moreover, each utility has its own configuration parameters. Although configuration parameters have improved the system, given the configuration parameters of the utility program, subtle issues may only manifest under certain conditions. For example, an issue in NTFS was triggered due to using check disk on the file system. The parameters involved were f from check disk and another unnamed parameter from Windows OS. The bug destroyed NTFS file system on SSD. Let's see another example. An issue in resize2fs is triggered only when two conditions are satisfied. The first condition is enabling sparse super2 feature while creating the file system image with make2fs. The second condition is to expand the file system image using resize2fs. This results in metadata corruption. Such configuration-related issues are difficult to test due to state explosion problem. For example, Ext4 has more than 85 configuration parameters with wide range of values, which leads to a huge number of configuration states. It takes a substantial amount of time to scrutinize the file system under each configuration state, which is practically impossible. New devices and advanced features only make the situation worse. Moreover, existing test suites have limited configuration coverage. For example, the default test suites for Ext4 and its utilities only use less than 50% parameters. We only considered if the parameter was used in the test suite or not for the configuration coverage, and not the combination of the parameters. Considering the combination of the parameters will make the situation even worse. There are limitations to existing research efforts. They mostly only focus on shallow configuration constraints, for example, spelling mistakes. They only consider multi-component configuration issues with shared configuration library. Some are not publicly available, and these works do not work for file system configuration issues. Here is our contribution to mitigate this problem. First, we derive a taxonomy of critical configuration dependencies. Second, we built a prototype to extract those dependencies, and finally, we integrated it to multiple tools and exposed configuration-related issues. In the next part of my presentation, I will talk about background, what configuration dependencies exist in file systems, how to extract and use multi-level dependencies, evaluation, and lastly, conclusion and future work. Let's move on to background. Many file systems can be configured by different utilities in 4 stages. In the first stage, we create the file system image using makeFS. Second, we mount the image using mount utility. Third, online tools such as e4defrag for Ext4 are used to make changes to the file system image while it is still mounted. The last stage is offline, which makes changes to an unmounted file system image. For example, resize2fs, fsek are some offline tools. We call the file systems and all the associated utilities used in the 4 stages as file system ecosystem to address the configuration challenge. Each utility is a component in this ecosystem. Configuration issues are not limited to file systems. Many existing work have looked into these issues. We follow the definitions proposed in other literatures. There are two important concepts. The first one is configuration constraint, which specifies configuration requirements in applications, for example, data type and value range. The second one is configuration dependency, which is one special type of constraint that describes the dependent correlation among parameters. For example, two parameters may manipulate the same variable, and through that they can have the dependency. This is critical for addressing complex configuration dependencies. But there is still limited understanding of these concepts in the context of file systems. This brings us to our first question: what configuration dependencies exist in file system? To answer this question, we now move on to the next part. We studied some important components of two representative file system ecosystem, Ext4 and XFS, to see what configuration dependencies exist in file system. We looked into their configuration related patches and source code. We performed configuration related keyword search, random sampling, and manual inspection, and finally got 78 bug patches. Our process is similar to previous relevant studies. We have 4 findings from our bug study. First, majority cases involve critical parameters to trigger the bug from more than one component. Second, a hierarchy of configuration dependencies exists in the file system. We classified the dependency in 3 major types. First, self-dependency, where one parameter in a component needs to satisfy its own constraints. For example, here block size needs to be in a certain range so that make2fs can run properly. Second, cross-parameter dependency, where 2 parameters from the same component are dependent on each other. For example, here resize inode and metabg cannot be enabled together. Third, cross-component dependency, where 2 parameters from 2 different components are dependent on each other. For example, here inline data from make2fs has dependency with the dax parameter from mount. These two cannot be enabled together. Enabling them together may result in data corruption. This table summarizes the multilevel dependencies we collected from our study of the bug patches. We see that 100% cases involve self-dependency and 96.2% cases involve cross-component dependency. Our third finding is parameters are handled in different ways in a file system ecosystem. They use 4 different types of variables to store the configuration variables, 2 ways to store parameters in the superblock, 2 different ways to load the parameters from the superblock, and various functions to handle the configurations. Our last finding is majority of cases do not require configuration specific workloads. This is the summary of the lessons learned from our findings. First, considering multilevel dependency is necessary. Second, heterogeneity of parameters make previous solutions inapplicable, so it requires new design to handle the heterogeneity of the parameters. From third finding, we see that existing efforts can be reused for stressing file systems. Next, we explore how to extract the dependencies automatically and use them to identify issues. To leverage configuration dependencies and address issues, we built our tool ConfD. It has 2 major components, ConfD core and ConfD plugins. ConfD core extracts the configuration dependencies and generates configuration states. ConfD plugins detects configuration issues using the extracted dependencies. For the constraint of time, I will only introduce a few components of ConfD. First, we have the taint analyzer. It generates taint traces to capture the propagation of configuration parameters. Our taint analysis is interprocedural, and context sensitive. It takes the bitcode of the target program and configuration variable as input, taints the source variable, taints the instructions along the data flow, and finally stores the instruction as a taint trace. We use the shared metadata structure to connect the components. For example, the parameter inode size is stored in the 27th field of the superblock. Other components such as Ext4 actually loads the parameter from the shared superblock structure and uses it. Therefore, we can use the superblock structure to make connection between make2fs utility and Ext4 file system. The state generator selectively generates configuration states leveraging the extracted multilevel dependencies. We build a tree with the dependency information of the parameters. For example, if we consider the parameter 64-bit, it has dependency with block size and inode ratio, creating 2 nodes from the root. We go to the left branch first and add it to the configuration state. Next, block size has dependency with 64-bit and bgalloc. Since we already considered 64-bit, we don't consider it again to avoid duplicate states and thus reducing the space for testing. We consider the next branch, which is bgalloc, and add it to the configuration state. We consider the depth to be 3 for our configuration state generator. The state generator has 2 policies. For following dependency, we generate valid configuration states. For violating dependency policy, we generate invalid states. The ConfD code requires 3 input from the user specified in one JSON file: function name as entry point, configuration variables and superblock, and command line syntax of parameters. This makes it more convenient for the user to provide input to the tool in a specified format. Next, we will describe the second part, ConfD plugin. We extend ConfD core using plugins. Currently, we have 6 plugins for Linux file system. In the table, we have the plugin IDs, the description of each plugin, base tool used, and name of the plugin. The first one is configuration specification checker, where we automatically extract dependencies from the man pages to detect documentation issues. Second one is misconfiguration handling checker, which uses the violating dependency policy of the state generator to see the misconfiguration handling of the target program. Plugin 3 and 4 are ConfD RFSEK and ConfD GT Hydra, which have 2 open source prototypes, RFSEK and GT Hydra, as their base tools. Plugin 5 and 6 are ConfD XFS test and ConfD E2FS procs, where we integrate ConfD with 2 regression test suites, XFS test and E2FS procs respectively. Next, we move on to the evaluation. We evaluated ConfD on 2 widely used file system ecosystem, Ext4 and XFS. We answered 2 questions. First, can ConfD extract multilevel dependencies automatically? Second, can ConfD help address configuration issues? To answer the first question, ConfD extracted 154 unique dependencies from Ext4 and XFS automatically with 8.4% false positives. On the left column, we have 2 file system ecosystem. For each file system ecosystem, we have number of extracted self-dependency, cross-parameter dependency, and cross-component dependency. The second question is, can ConfD help address configuration issues? The answer is yes. Depending on the plugins, ConfD can detect different types of issues. In the left column, we see different plugins, and in the right column, we see the types of issues identified by each plugin. Our plugin 5, ConfD XFS test, is based on XFS test, which is the test suite for testing file systems. ConfD XFS test checks test case failure with valid configuration. It also enhances the ability of the test suites by increasing the configuration coverage. This is one example from ConfD XFS test. With the default configuration, the test case in XFS test passes the test. But with ConfD XFS test, using our dependency-guided valid configuration state with bgalloc enabled, the test case fails. We further investigate the failed test case and found that running E4 defrag on a file system where bgalloc is enabled corrupts the file system image. We looked into the source code to find the root cause and found that it is already mentioned in the source code, but there is no documentation and prevention for this issue. In our plugin 3, ConfD RFSEK, we integrate our tool with RFSEK. RFSEK is an open source fault injector for testing file system checkers. It reports number of uncorrectable images under fault and observes symptoms. ConfD RFSEK improves RFSEK by using dependency-guided configuration states. In our experiment, RFSEK only showed one type of symptom of uncorrectable images, that is truncated file content. But ConfD RFSEK triggered two new symptoms, which are unmountable images and invalid file content. ConfD RFSEK generated more number of uncorrectable images than RFSEK. These results show that we can identify different types of corruption scenarios with ConfD RFSEK. In our plugin 4, we integrate our tool with GT Hydra. Hydra is an open source fuzzer which fuzzes file system images and checks number of issues triggered. ConfD GT Hydra improves Hydra by using its dependency-guided configuration states. We found that configuration GT Hydra triggered more issues than Hydra. Our plugin 1, ConfD specification checker, found 17 undocumented issues in the man pages of our file system Ext4 and XFS. In the rightmost column, we show the total number of undocumented or wrong dependencies identified by ConfD specification checker from different file system ecosystem. We also characterize them into different types of dependencies showed in the middle columns. We also compared our tool with Facebook Hydra. Facebook Hydra is a configuration management framework by Facebook. It generates different combination of configurations for different applications, where ConfD uses dependency information to generate configuration states. We considered 10 parameters from Make2FS and ran it in both Facebook Hydra and ConfD. Hydra generates more than 56,000 states, where ConfD only generated 30 states. Moreover, ConfD did not generate any duplicates or invalid states, where Hydra generated thousands of duplicates and invalid states. This is because Hydra did not consider any dependency information of the parameters, where ConfD used the dependency guidance to generate the states. The reduced number of states makes the testing of configurations convenient. In our work, we showed our study of real bugs and derived a taxonomy of configuration dependencies. We built an extensible framework called ConfD for addressing configuration issues and evaluated ConfD on Ext4 and XFS file system. As future work, we want to extend ConfD to support other file systems and other applications beyond file system, such as NDCTL and databases, to cover more issues in other file system and applications. We also want to integrate ConfD with Facebook Hydra and also CI/CD frameworks, so that applications that can be integrated with Facebook Hydra can be benefited from our dependency guidance information and use it as a service before using a program to avoid configuration related issues. Thank you for listening to our presentation. We have made ConfD accessible to everyone. We hope our tool could contribute to identifying configuration issues and make the system more reliable. I'm happy to answer any questions now.